This is Computing Up, conversations about computation writ large with Michael Littman and Dave Ackley. This episode was recorded January 15th, 2024.
Happy New Year.
Hey, Happy New Year, Michael.
How's 2024 looking for you?
Much like 2023. How about you?
I mean, I started it off with COVID. I got COVID on New Year's Eve. And so people kept wishing me a happy and a healthy 2024. And I'm like, I already
Too late.
Yeah, sorry. We'll have to try again in 2025.
Good for setting expectations. Is this the first time or the 12th?
Second time. I did summer of 2022 and then this one. I looked at a plot of COVID cases and I think I hit both peaks. Like there was a peak and then there was another peak, and I think those are the two times I got it.
Well,
so
I guess that would be the expected value for these sort of things.
That would indeed, yeah.
Yeah.
Case.
But in any case, it doesn't seem like you have any long symptoms at the moment.
I think my lungs are permanently damaged, but no, I don't have, like, I still can taste and smell. I still, oh yeah, and I can, and I have a cough. But like no fever or anything. It's all good. It's all fine.
Oh, it all is what it is.
So how did you have our last call was with Rich Sutton. That
right.
went well, right?
Yes, it was great.
It was kind of nice to reconnect with him after all these years.
Yeah, and it was kind of funny that we actually had a little disagreement about a few things. It was very exciting.
I wonder if anybody noticed that. I know you noticed that because it makes you uncomfortable.
Yeah. Well, at least one person mentioned on social media that there was sort of a little competition, fun. They said right. So. Who knows? Anyway.
Well, so Rich is at the University of Alberta, and our guest today is also at the University of Alberta and has some other commonalities with Rich Sutton. It's Martha White. Martha, thank you so much for joining us.
Thank you for having me.
It's so great. So Martha, I think of you as the first really important person in reinforcement learning who I didn't know. Like, I felt like, when I was coming up, there was a tremendous amount of excitement. There was Rich, right? So it was Rich Sutton. He was kind of alone. And then there was this kind of group that came in behind him in the 90s, and I knew all those people really well. We went all to the same meetings and stuff, and like I knew the field. And then all of a sudden everybody was talking about Martha White, and I'm like, who? Like, but Martha. I'm like, I don't think I know Martha. So it was the beginning of me kind of losing touch with the field. But
that was partially my fault, I'll add, because I felt the same about you, Michael. Everyone had met you and knew you, and I had never gotten a chance to meet you. And probably one of the reasons is just in my PhD, I worked a lot on unsupervised learning and semi-supervised learning, and was eventually drawn to the call of reinforced learning a little late. So we missed each other.
Well, so tell me a little bit about that. So what brought you to RL?
I mean, I wasn't.
Just to keep in mind, so Dave's dissertation, did it have reinforcement learning in the title, Dave?
No.
Okay. Right. It was a genetic machine for genetic.
Yeah, it was function optimization.
Right. But Dave had thought about reinforcement learning way back when, and when I started working with Dave, like, he kind of was my introduction to that. Like, it was something that I really wanted to study, and so I kind of latched onto Dave to kind of learn as much as I could. So that was kind of our connection with it. But how did you come to see RL? Weirdly, a lot of people start in RL and then run away to natural language processing. So you're like the opposite in a way.
I mean, automated decision making is a beautiful area to work in, and that's what reinforcement learning is all about. So it seems to me natural that people would gravitate towards RL. But then once you do gravitate toward, you see how hard it is. So I can also see how you would skedaddle. But yeah, so the way it worked for me is that I did my PhD at the University of Alberta also, actually, and I did it with Dale Shermans. And at the time I was working, and Michael Bowling, but I was largely working with Dale on, at the time, a big thing was convex reformulations of hard objectives. And that was a lot to do with semi-supervised learning and unsupervised learning. But of course, I was embedded in this larger group working on reinforcement learning. So I started working on reinforcement learning papers. And by the time I was done my PhD, I realized that's what I really wanted to focus on. But my first few years were very mix between representation learning and reinforcement learning. And, a lot of unsupervised learning is essentially representation learning. So I sort of brought that flavor to reinforced learning with me.
So convex representations of hard problems, was that the phrase?
I said
And
convex reformulations. Yeah.
reformulation. Okay. And so my notion of a hard problem is it's got lots of like spikes and cliffs and big flat areas with no signal and all that kind of thing. And that's what makes it hard to optimize or hard to represent cleanly. How
Yeah.
does convex reformulation change that?
Right. In my case, they weren't necessarily as hard as some of what you just said, but for example, they might be non-convex, so they'll have different local minima. If you can find a convex reformulation, so a way to re-express the problem so that it has just one nice global minima, or at least a region of global minima, then of course now gradient descent is just going to get you to that solution.
So it's sort of like a convex hull. If you have a knobby 3D object and you take a convex hull of that object, then in going in any particular direction, you can go as far as you want once you have the convex hull.
Yeah, sure. It is, that is related. That's fair
Kind
enough.
of.
Yeah.
Kind of. All right.
Yeah.
Just because, and essentially what that lets you do is go from one mountaintop, fly through the air to the next mountaintop without having to, or if you're in minimization terms, to just tunnel through the mountain to the next valley or whatever it happens to be
Yeah.
because you reformulated it. But
Tunneling
you
is a
might
good.
end up at a place that's illegal.
Right. And so in the examples you're looking at, that's absolutely true. And in some of the things we looked at, sometimes you actually change the problem. So now you're solving a different and easier problem. And then you just look at what the gap is between those two. So you'll always get to a feasible or reasonable solution in the new problem, but it wasn't exactly the problem you wanted to solve in the first place. Or sometimes you turn into a two-stage thing where they actually are equivalent, but you need to transform the solution back into the original space. And there's usually some gaps there, or maybe some infeasibility there.
I see. And then you just say, oops, we didn't work so good on this one. Yeah, if it maps back to something that's illegal in the original problem or whatever it is.
Yeah, that could be right.
Well, I don't know. I mean, I just, that phrase, I hadn't heard it before, so I had to bug you about it, but thank you.
Fair enough. But convex reformulations were all the rage in the, 2010s, let's say.
Yeah, machine learning is a very, I feel like, ragey kind of field, right? That there's a thing that everybody's excited about, and then people take, look at it from all the angles they can think of, and then somebody says, "Oh wait, there's something else cool over here," and then blah, 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 the field all kind of runs over there, and it's like, I don't know, support vector machines or whatever happens to be. So you're working with Dale Sherman. So Dale is pretty hardcore, right? Like, so he uses 8-syllable words, strung together all the time. And so that was kind of the world that you were growing up in. But it seems like being at the intersection of reinforcement learning, representation learning is a really exciting place to be right now. Is that right?
Absolutely. Although at the time when I was bringing representation learning insights, it was more things that were, again, older, things like sparse coding. I mean, I'm still a proponent of sparse representations for RL. It's one of the reasons I started working so much on that topic, is because I had been working on sparse coding. I liked those solution strategies, but very different from neural network strategies. So as time passed, and my initial work I wasn't working with neural networks at all. Shame on me. That was in like 2015. And then as obviously you start seeing how useful neural networks are. So I've started to keep still some of those insights, like how do I learn sparse representations, but now with neural networks.
And so sparse representations without neural networks is like Penti-Canerva or something? What are the techniques that people use there?
Yeah, Canerva coding is an interesting point. So for example, you could use something like RBFs or something along those lines, where you might find
basis functions.
or you might find like prototypes or central points, and only certain things are active. But that's not exactly a learning strategy. So sparse coding was actually trying to learn a re-representation that is sparse. But
so rather than saying my neurons or my whatever you're calling them are spatially limited, like a radial basis function or a Gaussian unit or something like that, and therefore just because they're scattered around in hyperspace, it's going to be a sparse representation. Instead of saying that, you're saying something like, well, we could have perceptrons or whatever it is, something like that, hyperplane-oriented stuff that is not necessarily sparse, but you're going to sparsify it somehow as a more problem level or architectural level rather than the individual decision rule?
Okay, let me see if I can rephrase that. So you're saying that neural networks, already neurons could be sparse. And now for sparse coding, how is that different? And you're saying that you might be in this higher dimensional space and you're going to try to sparsify in that higher dimensional space by just picking different components, for example.
something. Yeah.
Yeah, exactly. Yeah. So usually one of the ways sparse coding is explained is that you sort of have a dictionary of still something like representative points or parts of an input. And then the sparse part is that you get to subselect amongst those representative vectors and you get to linearly combine those representative vectors and you ignore all the other vectors. So the sparsity comes in almost like a selection and a reweighting.
So like k nearest neighbors or something like that is going to be a sparse representation if k is small relative to the size of the space or something like that.
Yeah, actually, I like the idea that k nearest neighbors could be thought of as a sparse representation because you're saying I'm going to put indicators that say these are the k things that are similar to me and zeros everywhere else. Yeah,
Right.
that could be done.
Well, I mean, it seems to me, the field, like Michael was saying, it's kind of slaps back and forth between being excited about A and then being excited about not A and then being excited about A prime, like that. And going back and forth, like we actually talked about Rich Sutton a little bit, the grandmother neuron back in the early days of everything, like how are these representations going to work? And the idea of a localized representation, like one unit, was the easiest thing to imagine. And we were arguing the connectionism that no, it had to be distributed. We didn't know exactly what that meant, but we knew the grandmother neuron was wrong, like that. And it really did seem that we've kind of oscillated back and forth, but kind of landing at, no, it's not really a grandmother neuron, but it might be a grandmother smattering of neurons that gets kind of the sweet spot between still having some separability, still having some orthogonality, whereas, and still having some generalizability, which is what the grandmother neuron didn't have. So is that get at what feels right about sparse for you?
Yes, absolutely. Yeah. Exactly what you said. I love the idea of having a huge space where you can have many, many things you could reason about, but for any one thing, you want it to be a smaller set, and it shouldn't just be one. It should be something of multiple.
Right. It needs to be a little compositional.
Yeah.
There needs to be some structure in there, but compared to the everything, it's like, like that.
So isn't this a battle that needs to be fought right now with regard to, say, like LLMs? Like, I feel like when people are probing what kind of representation these things learn, they're coming out with, it's totally unclear. It's just a big mishmash of everything. The same neurons seem to be used in multiple ways and multiple times. Everything's turned on. No one's clear on exactly how things are being represented. There's not only is there not a grandmother neuron, but like there's not even a grandmother pattern. It's just a mess. Is that accurate? And can we fix it?
I think this is a really good point. But I guess for me, it's always like, what's the purpose for your representation? Why do you even care to learn one if we even want to start defining one? But let's not go to the definition part of it. But to me, a large language model is one really large complex function. And, it's essentially doing querying. And maybe we don't care about how things are represented inside, other than, of course, we want to understand it. But whereas in reinforcement learning, if you have an agent learning online, for example, and it's constantly learning new things, encountering new things, that's where I think you really need to have a notion of a representation, something that the agent learns. It knows something about the world. You can think of it kind of like knowledge, and it's going to help it learn faster in the future. I know people are moving towards LLMs that are actually learning online, but right now I think of them more like large functions that are queried.
So you think that the difference here is that in the online learning case, the agent itself has to pick what to look at next, and that's why the representation has to be paying off sort of incrementally and from the get-go or something like that, as opposed to just being trained on the terabytes. It doesn't matter. Is that the distinction?
Yes, and to add to that a little bit too is that also when you learn online, we run into things like interference with what you've learned before, and different types of representations can be more or less prone to interference.
Right. And I mean, it seems to me the whole continual learning or online learning and the catastrophic forgetting and all that stuff, I mean, in some abstract principle, it's completely hopeless. Because, how do you know whether the old thing is no longer useful and it should be forgotten, or the old thing might be useful and it just needs to be tweaked? And do you think there is much sort of general juice that can be pulled out without having to say, well, in this particular case, this historical stuff is relevant and that historical stuff is not?
I think this is a great question. And it also comes back to sometimes we do want to forget. So like we can't remember everything. I have no answer to this question, but I do think we have a slightly different question to answer right now is that we don't even necessarily know how to control the forgetting. So at least if we knew how to identify what to remember, it would be nice to be able to learn our networks in a way that doesn't forget. So like one example is you can often take a network and train on everything all at once, and it can perfectly learn something good for all of that. So somehow it learns some general purpose solution, but if you do it sequentially, it doesn't. So it's not even a capacity problem. We don't have to forget anything, but our sequential learning algorithms are not learning that same solution. And that feels almost solvable. Also, maybe asking for a little too much, but a little bit more solvable.
I mean, does that suggest that the learning algorithms we're using are throwing away their degrees of freedom way too fast? That they're overlearning the first whatever you show them, and because they're completely too eager, and an epsilon of 0.01, there is no epsilon, which is gonna learn a little bit but not learn way too much. That kind of problem?
Yeah, I think that's right. It's overcommitting to one direction, and that area is not useful for learning everything.
Right. And once again, in the state of nature, you just have to be good enough. You just have to survive. You just have to get through it. And it doesn't matter how much of a big of a hack is, as long as you're on the right side of the survival curve, like that. But then we don't know when we're trying to do more general stuff, learning, how do we pick that line and so on. I guess it still comes down to you got to try sample problems. And see that whether you're working and so on.
So maybe that gets us into meta learning. Like,
go ahead.
I know that's a topic that you've engaged with. What's your current thinking about meta learning? Is this a solved problem? Is this a unsolvable problem?
What does it even mean? What does meta learning
and what does it mean?
To me, meta learning means, I would also love to hear what your guys' definitions are for these things. But to me, meta learning means that the objective you're trying to optimize is future learning. Like, you want your updates now, or whatever it is you're optimizing to help you learn faster in the future. And sometimes that might mean you actually change your objective. So in traditional meta learning, you actually go get, your test set or test problems, and you try to do gradient descent through all of that, where you see updates over here on training. Does that improve on test? And in some sense, your objective has changed to accuracy on test rather than minimizing a training loss. In RL, it's a little more complicated, of course, since we don't have tests, but I think the goals are still the same, is that you want your updates now to help you learn in the future.
And yet, right, okay. So instead of just doing better on the immediate problem, you want something. I mean, if the future is exactly the same as the present, then there's no difference. You just yes, learn.
That's
so
right.
There has to be some implication that the future is going to be different somehow, and we would like to figure out how. We would like to predict the change. Is that what it's trying to do? Is that what makes it meta?
Or figure out what's the consistent thing across all these different problems.
What you're right.
And
which
cash
part?
that out, right? Make that no longer adaptable, and then keep your adaptability around the things that are going to vary from problem to problem.
Yeah. Or it could also be that you try to do things now that preserve the ability or improve the ability to learn later in terms of, for example, exploration, or even the direction you do gradient descent. So like, I think for meta learning, a common thing, if you think about representation learning, would be to say, how should I change my neural network now so that when I continue to do gradient descent from this point, let me see if I can say this. So I'm going to start at a point with my neural network, then I'm going to do gradient descent for a few steps, and I want to know how accurate I'm going to be on test data. If you do meta learning instead, you might say, I want my neural network to start at a different place so that updating on this data generalizes better to other data. So you're trying to optimize for generalization rather than training error. Or in RL, the one I would be most excited about is meta learning exploration. Is there a way that you can learn, like doing certain exploratory things now makes it so you learn to, like you're essentially learning to explore, so that when you see new things, it's not that you anticipate what that new thing is. You've just learned general purpose exploration strategies.
And how could you identify such things?
I have no idea. Actually, I've never worked on exploration with meta learning for exploration.
But it would be
I just think it's important. Yeah.
Uh-huh.
There are papers that talk
There's
about
papers
this.
on it. Yeah.
Yeah. And so sometimes it involves things like changing the reward function over time, right? So what your meta learner learns is a non-stationary reward function that tends to guide you towards learning the things you need to learn when you need to learn them, right? So it's not like a fixed learner anymore. It's actually a dynamic learner, and the parameters of that dynamism are are trained or meta learned.
Right.
Or another one you could imagine as well as one thing I have thought about a little bit is intrinsic motivation, like adding, having the learner reason about its own learning. And there you could have a meta learner that's essentially recurrent on some kind of learning signal. Like maybe it has errors that are being outputted. If those errors are small, maybe it spits out a low exploration rate. If suddenly something changes and its errors get high, maybe it tries to re-explore. So you can imagine like a recurrent neural network on your own errors, trying to guess or predict like what would be a good exploration rate.
Well, that sounds cool. I mean, certainly, if there was some way to say, rather than there's some Shannon information of meta necessity, you just say, I just surprised myself because this was much better or much worse than I expected. So that is just first principles interesting, and I need to go represent that. I need to go do some more search there or whatever the hell it is. Well, that would be good. And I mean, all right. So representations, it seems to me representations are the guts of everything, which is on the one hand very powerful, but on the other hand, it means saying representations by itself doesn't do very much for you. And sparse representations, yes, absolutely. Just as a sort of practical matter. So I looked at a couple of your papers, just briefly trying to understand who you were. And so I get this OML thing, this online aware machine learning, on a online aware meta learning. Is that what it is?
Meta learning.
Okay. A meta objective that uses catastrophic interference as a training signal. Is that what we're just talking about here? Or is that, a down payment in that direction?
Yeah, that's absolutely a meta learning strategy. We're trying to reason about how do I learn representation that interferes less.
And how do you detect catastrophic interference?
Oh, yeah. So in that work, we tried to give some measure of interference. It was really just based on TD errors and trying to estimate errors based on Bellman errors. And we acknowledge it was relatively limited.
Well, I mean, that's fine.
So the answer is it's hard to measure interference, actually. So there's been some proposals, and yeah, we're still early days on really understanding how to measure it.
So
it sounds like a very empirical way to do it, is just to say, well, if it's been interfered with, like if it's actually degraded in its performance, then
that's interference.
That must have been interference. Yeah.
Right. Yeah.
And could it be the case that non-catastrophic interference will just average out in the noise and only the big errors will remain, and that's why you hope to follow that the TD errors, or whatever it is, I don't even know what those things are anymore, the Bellman errors and all that stuff. The bellman at the front door, right?
Not that one. It's Richard Bellman. It's a rich Bellman. It's a Bellman who actually has a lot of money.
So he would have a front door with a Bellman.
You're right. You'd have the Bellman would have a Bellman. Yeah.
The Bellman would have a Bellman. Like that.
Yeah. So you're right that you might want to average your errors across some amount and say, on average, if it was kind of low, then maybe you're not too worried. There's always going to be some interference, and you want to focus on the higher levels of interference.
And I always wanted to have the cases where we didn't have to measure the interference. We could just work incrementally and then observe that it works out to be focusing on the big interference, because the little stuff all washes out, and the bigger stuff, kind of like doing momentum in learning and that kind of thing, that it actually sort of figures out the downhill vector, even if it is kind of sloshing around during the learning. And it could do the same thing with this meta learning as well. Actually, this is an argument Michael and I have had a few times about, in reinforcement learning, does the reinforcement signal need to be reduced to a scalar? Do you actually have to come up with a single number, yes or no, or more or less? And Michael always seemed to think, well, that was fine. And that always bugged me, because I didn't feel like, in my head, I felt like there were all kinds of sub-signals and stuff that only came together a little bit, or only came together if they had to. And the rest of it would all work separately. I don't know if maybe meta learning could have something to do with that. I don't know. Does this make any sense?
Maybe Michael and I have a similar opinion on this. I'm not sure. But if I were to point to my own head and agree that it seems like it has the properties that you just said, I might call that part of the solution. So I believe we probably have sub goals and we have intrinsic rewards, but I wouldn't call that the reward. So there's the reward for me probably survival and other things. And then I have for my evolution or me or whatever, have created a bunch of internal rewards that are only active sometimes, only relevant to some sub goals. And the solution has this property, but the actual problem has one scalar reward. And so meta learning could be seen as evolution to some extent, as the thing that has built all this stuff into this solution, which is me, my brain.
Uh-huh. Yeah. So you're saying that, in the biggest picture, like survival or whatever it is, there might be some kind of abstract Platonic reinforcement signal that doesn't actually have to be reified in any particular physics, any single cubic centimeter of brain or anything. It's just, survival and all that stuff, and we can talk about it, even though it doesn't. But once we have these proxies inside our head, those things are physical. Those things are representations inside some computing architecture, inside the space that we control in this little universe. And so even there, I want to object to saying that those things are scalars like that. Do you think they are, or do you think it just doesn't even matter?
I guess I do think they're scalars, but now I'm just thinking about why I think they're scalars. Why aren't they scalars?
Well, to me, so I work on distributed representations and spatial computing, where you think that the rate of communication between zillions of things is relatively slow compared to what you would like to get done. So you have to make stuff be locally represented. And to me, the cost of pulling all these signals together in order to come up with a scalar seems like a big deal. And I would much rather just bring it together at a smaller scale and say, okay, that's good enough, check, uncheck, and then go back like that, and never continue up to ever develop okay, right now in our entire life we are at 27.2 or whatever it is. Does that make any sense?
It does make sense. Although I could imagine that, in this beautiful distributed system where maybe each of these are their own little agents even, or they have their own goals, rewards, and so on. There could still be some kind of global signal that takes longer to propagate and eventually kind of pushes them in the same direction.
Sure. Yeah, that's beautiful. So we could say reinforcement is a scalar in the limit. See, I would be okay with that, saying that, at the biggest scale of our entire brain, which might have an integration time of, who knows, seconds or minutes even, or whatever it is, that we could imagine that there could be a overall integrated value that has a number, has a factor. It's positive, it's negative, whatever. Even if the sub goals or sub agents or whatever it is have the complete opposite at the moment, they're thinking up, down, and so forth. It just hasn't propagated yet.
Right.
But there might still be up at the very top. Maybe, I don't know. Okay, all right. Well, but thank you for engaging with me on that, just because it's something that. Yeah, that like I said, Michael and I have talked about it, and I still can't quite get my head around it.
Yeah, certainly. So Rich Sutton in particular is an advocate of this notion of it has to be a scalar. It wants to be a scalar. It's just otherwise, how are you making decisions? But I like thinking about it in terms of this distributed system, as the way you're describing it, Dave. Because if you think about I don't know, like global human activity, right? Like there's. Right. I make some decisions. Maybe I have a scalar, but then at the level of my family unit, maybe there's a different scalar that we jointly somehow are optimizing.
No, Lisa has it.
Or my wife. Sure. But then the community, and then the region, and then the country, and then the world and whatnot. And that you can talk about the world's reinforcement scalar, but it's not being moment to moment optimized. It's being acted on in a very distributed kind of post hoc way. Huh.
Right. And likely quite suboptimal, but maybe there is one.
Likely quite suboptimal. Yeah, that describes humanity in a lot of ways.
Oh, I want to speak up for humanity here. So then the other half of my story is fighting for robustness over efficiency. And so when I hear about people optimizing stuff, in my mind, that invariably means they're flushing out redundancies. They're making the answer as pure as possible with no waste, saying, I didn't compute this number twice. I just computed it once because it's faster, it's more efficient, that kind of thing. I felt like I grew up being an efficiency hound, just like almost everybody in computer science does. But then I started thinking about, well, what if there's errors? What if execution is not deterministic? And because in reality, it's not, especially when computations get really big. And so as a result, I started thinking much more about robustness, about stuff that has a nice flat landscape. So even if you completely screw this up, you're going to end up at almost the same place, like that. And that's a valuable thing, even if it's strictly suboptimal, because you didn't actually climb that little teeny peak that you could have, but then you would have been next to all these cliffs where if you moved in the tiniest little bit, bam. But I would think your feeling would be, you'd say, well, but we want it to generalize. And if we want it to generalize, then it will be robust. So how does that come along with optimization?
Well, this is not the area I work in, but there are some really great results in the last few years about how our optimizers, things like stochastic gradient descent, do seem to prefer flatter regions, not these kind of peaked regions.
Right.
And in fact, it does. Getting to those flatter regions seems to generalize better. So like there has been all this anecdotal evidence that stochastic gradient descent neural networks generalize very well. What's going on here? And it does seem like it's related to robustness, like you're saying.
Yeah, I guess so. I mean, that's a good example, right? Because the stochasticness of stochastic gradient descent was kind of just a hack. It was kind of just, we have too much data. We need to get some signal. We need to parallelize the whole thing. So we'll give everybody a random 100 samples and then so on and so forth. When that has the effect of adding noise to the learning signal that anything sees at any given moment, so that if you are on one of these little peaks, you'll get knocked off. And so that necessarily you're going to have to be on a relatively flat area. But at least at first, that was not the point. That was just kind of a side effect.
Yes, definitely a side effect.
Whereas it could be the point, and
Right.
maybe it should be. Maybe that's what people are saying these days. I don't know.
Right. That's what I'm hearing, is that there's a recognition that there's a bunch of things that gradient descent does that aid in, for example, resisting overfitting, right? That
Right.
used to be, overfitting was like the scariest thing. And now people are like, deep learning, it's probably fine. You can't really overfit because it'll do the right thing. And I think that's partly because of there's properties of this algorithm that are beneficial that maybe weren't really designed in. So stochasticness maybe is one of them.
Right.
Starting with really low weights, I think, turns out to be one of them too. Like the fact that we're not willing to wait forever, like run the thing forever, helps keep it in a part of the state space, the weight space that generalizes better.
Because at least a traditional sort of sigmoid something or other is pretty smooth near the origin, like that. And so you've got you're not throwing stuff away just being pinned until you actually drive yourself there.
But I kind of like Dave's point here in some sense, is that maybe this isn't your point, but you're sort of saying that we're still not really taking it that seriously, is that we accidentally
his point.
Yes, that we got this property accidentally. And it's definitely the case that we can't say for sure it happens everywhere. And I don't know about you, Michael, but definitely some of my groups still find that neural networks don't always have these nice properties. Sometimes they do overfit. And so
Right.
yeah, maybe we should be thinking about it a little bit more.
Well, I mean, so a related example. So I saw a phrase in one of your papers that said, sparsity promotes locality, like that. And then in my head, I was like, well, what about turning that around? That, locality promotes sparsity, because I'm doing this spatial computing stuff, just as we discussed a few moments ago, where if I can keep things spatially local, it's better because I don't have to do all this communication and everything is just much better. And then automatically it becomes sparse because it can only respond to stuff it sees here, stuff that happens over
the
there. It
neighborhood.
cannot possibly change what this thing does, at least not directly, like that. And what I'm wondering is, is there maybe this kind of bottom-up robustness first story that includes things like be random and be spatially local and all of this stuff that are going to end up doing all this great stuff for the top-down fitness function, optimization, so on and so forth? And if so, is there some way we could accelerate that process rather than kind of always coming from the top and only grudgingly doing the important thing, which is be random and so on, or be spatially local and so on? You see what I'm saying?
I think I do. I think maybe one of the issues sometimes is that when we try to, you guys did just talk to Rich, and he is, of course, the author of The Better Lesson, but it does seem like sometimes when you try to build in these things that give you these nice robustness properties, sometimes the alternative was to do the simple thing of, like learning a bigger model, lots of data, using a simple algorithm, and then we get the natural robust solution rather than the one that I thought would be robust. And so I think it pushes us away from developing these robust things. But
yeah, well, so that to me, the key there is the word simple. That you say you do this simpler thing, whereas like being robust is more complex. But it might not go that way. It might go the other way around. If you're saying I'm building a computer architecture that is infinitely scalable, you can add more tiles to it and grow it and grow it and grow it. That implies a bunch of constraints on how they're going to work. Like they have to be connected locally. There can't be long distance connections. All of this kind of stuff. But it's very simple in a way, because once you have a tile, you just put more and more and more and more,
Right.
and off you go, like that. But it's a very different notion of simplicity than saying all we need is one array, all we need is RAM, and we'll do a all-to-all network, and we'll be done like that. So I don't want to give away simplicity.
I want to say
the
simplicity is not a scalar.
I want to say simplicity is derivative from architectural assumptions you make. And so once you say like CPU and RAM, or once you say deterministic execution, then that implies a certain kind of simplicities make more sense and others don't. But I'm just saying, well, there's room for other architectures which might have these robustness features. Those might be the things that are simple in that architecture.
right. I also kind of love the idea of having spatial locality be a mechanism where you restrict yourself in what you can do.
Right.
When I said the word locality, I almost meant that when you learn a representation, a sparse representation, you get a notion of distance or similarity, and you're going to have much more clear clusterings or groupings when you have sparse representations rather than these big, dense vectors. Right. It's sort of harder to get a meaningful distance. But nothing we did was spatially local. It was sort of implied local in this new space. So what are your thoughts then about enforcing spatial relationships?
Well, it brings it's a great introduction, because it brings me to another one of my hobby horses, which is fully connected layers, and that what's up with that? That's too expensive, like that, and that it's the fully connected layer that allows you to come up with a sparse representation that is not spatially local, because you could have those things going from anywhere to anywhere, from one layer to the next, like that. And what I want to say is, couldn't we figure out some way that we would incrementally swap your weights around, do editing on your thing to make the things that are spatially local in the embedding space, in the problem space that you're thinking about, make them be local in architectural space as well, make them move together? Because I have to believe that's going to do all kinds of good things, for generalization, for everything.
Right. In some sense, I guess CNNs give you some kind of the spatial locality and groupings that you're talking about.
Yeah, it's an awful big hammer to say, okay, everybody, like that. And there needs to be something in between fully connected and CNN, I guess.
Right. My group has been working a little bit on not just sparsity of activation, but also sparsity of connectivity, as are many people. And there are some interesting strategies around pruning and trying to get sparse layers. And I think you're particularly sparse connectivity, and you're particularly talking about making sure that you actually have groupings as well, so that like the connectivity has a structure to it, not just randomized anywhere connectivity.
Right. Yeah. And it ought to be the case, it seems to me, that we can over parameterize the networks badly, hugely enough, as we do, that saying that each layer only projects to a spatially contiguous layer downstream, so you'd actually have to move through, K layers before you could actually get an equivalent all-to-all connection. Shouldn't kill us like that. It'll make something more inefficient because the long distance dependencies, as opposed to merely the higher order dependencies, are going to be harder to find. But it's going to I guess the point is that then we actually want to spatialize the input representation in some problem sensible way rather than just saying it doesn't matter. So we put all of our inputs in a big vector, and because that's again counting on a random fully connected thing to remap them. I don't know. I don't know.
Yeah,
Speak.
I'm a big proponent of sparse connections and networks, and I do think the community is moving that way. Like, the larger our networks, the
Right.
more that's going to make sense.
Right. And so like I'm working again from bottom up, where I essentially am doing a cellular automata model where you have like a Manhattan distance 4 around yourself in order to decide what your transition function is. And that's it. And if you need more than that, you have to implement it, which
Hmm.
you certainly can, but then you're paying like that. And so, locality, check. Really, really wicked locality. And it turns out you can do all kinds of things with it. It's just a very different kind of programming, a very different style of programming.
So, Martha, one thing I was wondering about is that we're now in a new year, 2024. 2023 was a really interesting year from an artificial intelligence perspective. How'd you do? Like, what was it? What was your journey like, and where do you see yourself going in 2024?
Yeah, so I guess 2023 was very interesting for everyone because everything was upended by large language models, is presumably what you were talking about.
Yeah.
Um,
Well, that
I,
and just the fact that the word AI now and
Now it's
machine
an
learning,
official thing.
yeah, people like I can't take an Uber ride without somebody starting a conversation with me about artificial intelligence, not knowing that I've been doing this for 30 years. It's just it's in everybody's air now, and
right.
that's really interesting.
Right. I guess the way that it impacted me for the last year is one, just like everyone else, I was shocked and surprised at how good large language models were. And just like others had some skepticism about it, but continued to be surprised and amazed as time passed. So I think it was a great demonstration of what you can do like with that. So that was amazing. Other thing, of course, is that probably just like yourselves was asked to sit on more panels and talk to people more about AI risks, what's good about it, what's happening. So a little bit of that. Like the research in my group didn't change much, but I am starting to work a bit more on applied projects. So I've been reaching out to different groups to see how can I use RL for industrial control.
Oh,
That's
nice.
because I think that's a great use case for reinforcement learning. And I feel like there's more interest because everyone's heard of AI. They're realizing the need to understand what is even AI. So they're more interested in working on with me for AI for industrial control. So largely positive. My students
So
haven't freaked out, which is good because I've heard some students have been freaking out. At least I
Yeah, I
don't
don't
think
know.
my students have freaked out.
Have you seen the there's an article that people were passing around, I think it was on Archive, which was something like advice for depressed academics around
Yeah,
AI,
yeah, I
something
saw
like
that
that.
one.
And so it's like, yeah, a lot of people were having that kind of reaction. It's sort of, oh, this really is an existential threat, but not in the way they're saying. It's more like it's like my career feels like it's existentially threatened.
I think, well, okay. 2023 didn't seem all that amazing to me from an AI point of view. Although, I mean, I was a curmudgeon. I was slow to actually try large language models for anything. And now I admit, yeah, they can answer some questions faster than straight up searching. But then they lie. And so I tended to go to them with a little bit harder questions. Like
Yeah.
the example I gave was that there was I was trying to figure out how to use this robot environment, Mujoko, which is
Yeah,
one of these
that's a thing.
gymnasium things.
Yeah, we're
And
familiar.
Yeah, and there was a package, Mujoko Pi, that had all of these wonderful tutorials and all this great stuff. But now DeepMind came out with a Mujoko package that was not Mujoko Pi, that was really low level and just the guts and everything, better to build on, but no documentation, no tutorials and everything. So I was trying to start in with the new Mujoko, and so I would ask the large language models, please tell me how to put up a display window without using Mujoko Pi. And it says here's how to put up a display window without using Mujoko Pi. Step 1, import Mujoko Pi. Like that, and it didn't give a crap, because the statistics were sure that, oh yeah, the right way to do this is say don't use Mujoko Pi and then use it.
Actually use
it. So I gave up on that. I mean, if, there's lots of easy questions and maybe it's easier than searching, I don't know, whatever.
Yeah, I don't personally use it myself,
ahead.
but I do get that others have given me examples of where it has been very useful for them. But yeah, I don't use it myself.
Yeah. I guess we got a little time still. So industrial control. So this is like the chemical factory and the steam pressure and the valves and
Exactly.
Chernobyl, and you're going to say open valve 3 using AI?
Yeah, except for I'm working on drinking water treatment, which sounds a lot less scary than what you just described. But
I see.
Or
So-
more
so
scary because people are going to drink it at the end.
Yeah, everybody's going to drink it, and you can't avoid
Better
going to
not do something
Chernobyl.
bad.
the beautiful thing about drinking water treatment, which is one of the reasons we chose it, is that you can't really harm anyone. The filters are very good. The water comes through and it's going to be clean on the other end. All you can really do is waste energy, waste some chemicals. So our goal is to use less energy, use less chemicals.
I see. And I don't know, there's these stories in the last couple of weeks about putting all those billions of nanoplastics in the bottles as well to make it more, I don't know, helpful for turning us into plastic.
There's definitely some cool research going on in drinking water treatment around like getting rid of these PFAS and all that stuff. But
Right,
that's not an all. It's not really an
Yeah.
RL problem right now. It's more of a chemistry problem right
Well,
now.
and so my question is I sort of would imagine that an actual real factory with, turn on the chlorine and turn off the whatever you've got, would be a more conventional control problem, that you would use more conventional control system stuff, and you wouldn't need reinforcement learning. Where do we get a case where just, dynamic programming doesn't do it?
Right. I mean, process control is obviously been automated for many years. Engineers have been working on this for a long time with traditional control methods. So obviously they have some reasonable solutions there. But the reason it really comes in nicely is right now there's a lot of human in the loop for these kinds of factories or places. You'll deploy a solution. For example, you might use this thing called model predictive control. Engineers sat down for 4 weeks. They built some really awesome models. Those models are great for 6 months. Then the system drifts and changes, as all physical systems do. And then those models either have to stop being used and have to change to some other strategy, or you kind of have to have someone tinkering all the time.
I see.
And so there's a lot of tuning by people, or there's not, and the system just runs suboptimally. So
Right.
it's one of those two things. And so it seems pretty clear to me that you could layer on top of what they already have. Like they already have a good interface. There's already some robust control in there, and you could just sort of be tuning those existing controllers to be more efficient. So it's not really a wholesale replacement. It's more of a replace the humans that should be doing the tuning with agents that could be doing the tuning.
And so is it one of these non-stationary reinforcement learning problems that exactly is the stuff your groups have been working on? And so the idea is that a month from now we're out of policy just because the pump is worn out or
Exactly. Or the
whatever
filters
the heck
degrade over time
Right.
always. Yeah.
Right. And so at the very least, you could maybe keep it running in a good window longer, so it would have to be tweaked less, or something like that. And is this an abstract theoretical thing, or is
No,
this?
we're actually working with a real engineering company in a town. We have a system there. We've been trying to get RL to work on that real system.
Cool.
That's
Oh,
awesome.
do
You
they
can
have
really make quite a splash.
Yeah, it's been a great project for grounding my research because even though, it took a while to actually build the system, start doing things ahead of time for at least a few years, we started thinking about what would we really need to do to get RL in the real world. And then you remember that you're not working on the right problems. We weren't working on hyperparameter selection. And how do you run an agent on the real world if you don't know what hyperparameters to select? And we weren't thinking about how do you not learn from scratch? If you don't have to learn from scratch, you should definitely not learn from scratch. So we started working a lot more on how do you take existing data,
Right.
initialize your agent however you can so that it can start learning from a much better place on the system and so on. So yeah, my research has definitely been impacted over the last few years.
Does that tie into the meta learning thing to some degree? Because you're really thinking of the problem in a more, I don't know, sort of a broader space, not just you wake up one morning and someone drops a problem in your lap. It's like there's relationships between the problems that are being solved.
You're right. It should have been that, but actually I was working on meta learning before, and then I haven't really looked at meta learning for this, but of course, meta learning isn't going away. So we've been thinking about how we can use meta learning to do some of this offline training for sure.
Got it. No, I think it's super fascinating. So when I was at Rutgers, I named my lab the Rutgers Laboratory for Real Life Reinforcement Learning because that spells RL cubed. But the real life part was to try to encourage the students, let's not just take the latest simulator, the latest pole balancer or whatever, and try to
Mujoko.
Yeah, take Mujoko. But like to have problems. Well, yeah, Mujoko's better than it could be, but it's not good enough.
Yeah.
And so connecting with a water treatment plant, man, like that would have been the dream back then. I'm so glad that you're looking into that.
So did the water treatment or the plastic, the bottle factory, whatever the heck it is, did they already have a simulation that they'd built that you could use, or did you actually have to build that up?
We had not built a simulator, actually. What we had done initially is we had their data from their main plant, and we tried to build a simulator, and we ran into the problems that almost everyone, I think, runs into, which is our simulator was bad and we couldn't roll it forward very far. And we tried all the usual tricks, like train through multiple rollouts and so on. And eventually realized that actually we'd like to pursue a direction that involves no simulator. Like, we don't need to learn a simulator and train RL in the simulator. Let's instead try to do different strategies. So like, why not just use offline reinforced learning and train directly on the data, and then reason about how we can get our online agent to continue learning online, not with no explicit simulator learned. The agent itself might learn an internal model, but I wouldn't call that a simulator. That's just a model-based RL agent.
Right. I see. And so the point is, then all you've got is their historical data, and you can slice and dice that various ways to try to find out how your learned model is working.
So the beauty for us is we actually have a physical system that is not their main plant. We have a smaller version, it's like a pilot system. And
there's the simulation. Right?
Yeah, exactly.
Yeah, that's right. So we have a physical simulator, I agree. But nonetheless, even for the physical simulator, you end up running into some real world problems. Like we can't just do whatever we want. We can break that thing too, right? And the filters cost money, and so but absolutely it makes it a lot easier.
But you could deploy on it and see how it actually works.
Exactly. Without affecting the town's drinking water or causing their system to shut down or something. Yeah.
And have you done that?
Yeah, we've been deploying stuff on it.
Oh, cool!
Wow.
And are they happy with you, or they say, "No, you ruined the filters again"? Or
no, so far it's been good. Actually, their system's quite good. So some of our initial tests, which we ran in the winter, apparently the water is very clean in the winter time. So some of our initial tests just showed very simple solutions. Yeah,
right.
Bring the chemical dosing down very low because you really don't need it. The water is so clean, and there wasn't a lot more to optimize there. So we're setting up to do more tests now in the spring where the water conditions are more challenging.
How well did they know about collecting the kind of data that you would need, right? Because this is something that I feel like I run into all the time, that people are like, oh, we've got data. And then I look at the data, and it's like, this is not helpful from a reinforcement learning perspective because there's really no way that you could do any kind of what ifs. There's just, it's the wrong data. The wrong things are being captured and the wrong things are being experimented with. How are they savvy about that, or are you able to teach them? How do you?
They haven't collected the right data. I agree with that. I have definitely learned that in process control, offline data is only going to get you a very small way forward because the strategies people use are very narrow. They're trying to regulate the system, keep it behaving exactly as it's behaving. It's very hard to do what ifs. But at least one thing that's nice about this is that these places are reasonably well I guess not automated isn't exactly the right word, but they've been digitized for quite some time. So they do collect data for multiple years. They collect them at a rate of like at least every 15 minutes. And you get to see what the operators do at least. And they have some variability in what they do. But yeah, definitely, I think that's one of the reasons we really need online RL in this scenario. There isn't enough variability, and the agent's going to have to do a little bit of learning on the system itself to supplement that.
Awesome.
Oh, super cool. So Martha, this is a whole lot of fun. One question I like to ask people at the end is, what are we missing? What is the whole field missing? Well, what other things should we be thinking about that we're not thinking about?
I mean, there are many things, but I think probably the most important thing. Okay, there's a couple of really important things. One right now, I think, is that we really don't have agents that can actually run on real systems. So our agents have so many hyperparameters. I know this seems like very basic and obvious and shouldn't be that exciting, but honestly, it's very hard to take an existing agent and just run it on a new system. It has so many hyperparameters, and those hyperparameters are finicky. And you can't tune those hyperparameters on a real system. You can't just run 20 different hyperparameter settings on a real physical system. That is not allowed. So I think as a field, we really need to work on that more if we want our algorithms to be used. And then I think the other one that is interesting is we're still working a lot with just model-free agents, or maybe sometimes like these world model-like agents where you learn this big transition dynamics model. But we're asking a little less, how can we use modular components to learn about the world? So like planning with options and like reasoning, thinking more about actually how should agents reason. So I feel like we're missing that a bit in RL right now.
Well, it sounds kind of like the AI critics who say that the large language models, what they're missing is reasoning, like that. And, sure, in the end, it all has to come together. It's, how can we get there? How can we turn the crank? Well, I agree. It seems to me that, especially, all the hyperparameters going to the real model, I would say what we need is more robustness, robustness to transfer, amongst robots or from, Mujoko to a robot or whatever the heck it is. And, maybe give up a little bit of optimization in order to get that, like that. Well, so again, hadn't met you before. I really enjoyed the conversation. Martha, thanks so much for joining us.
Me too. It was very nice to meet you. Nice to see you too, Michael.
Yeah, awesome. Thanks for being here.
This was Computing Up. Thanks for listening.